Hey there, Chad. So normally, without considering any of the perturbations, our H naught is successful in describing our system. But if we want to account for interactions such as nuclear spin, we have to introduce the I dot J term here you see in the Hamiltonian, and other terms such as like an external magnetic field, we need to add this term into the Hamiltonian, both of which perturb it a bit. Luckily, we can make the approximation relating this G sub j term to G sub L plus G sub S, so that we can combine these two operators, L and S, the angular momentum operator and the spin operator, into the J operator, such that L, S, J, and M sub j are all good quantum numbers, and we could describe those all with that single ket.
Now that we are counter-introduced as our new Hamiltonian, I just wanted to point out a few things that our I dot J term actually does produce good quantum numbers because F squared, I squared, and J squared all commute with the Hamiltonian. And what also that entails is that a good quantum number is a number in your ket that corresponds to an operator that commutes with our Hamiltonian. So, for example, if I operate if this was only our Hamiltonian, let's say our magnetic field was 0. If I operate this Hamiltonian on this, on this representation, my F squared operator will pull out an F times F plus 1 times H bar squared. So that's just kind of an overview of what a good quantum number is. But unfortunately for this problem, we do have another term. We do have a J dot B term, and our B field is a constant in the Z direction. So what that does is that kind of makes our Hamiltonian not have only good quantum numbers. And so basically what that does is that when we operate our Hamiltonian on our states, we do not get all eigenstates. For example, if we operate the Hamiltonian on our second state, which I defined the second state as this superposition, we get a constant on 2 plus another constant on 4. So we do not have the eigenvalue problem here, unfortunately. But that is okay because with degenerate perturbation theory, we can still find the perturbed energies of this state by making a 4x4 matrix that consists of all sandwiches of all these states, which we will do in the next part.
Yee-hoodly-doo! All right, so since we have multiple states all within the same n energy value, we call those degenerate eigenstates. And so we just went over how Michael computed the Hamiltonian acting on each of these product states, eigenstates. And so we're going to use those to make the sandwich of the matrix like Michael briefly mentioned, and we do so by creating our bra and ket sandwiches such that 1 and 1 is sandwiched on the top left, 2 and 2 on the next diagonal down, 3 on 3, and 4 on 4. You can see that we have some off-diagonal terms in the sub 2x2 matrix here. It's a convenient way to write our matrix this way because we can simply find the determinants of this sub 2x2 matrix, and this sub 2x2 matrix. The top two eigenvalues are the easiest because we don't have any off-diagonal terms. So if you were to take the determinant of this, you'd get these as your eigenvalues. So they're just simply the eigenvalues on the diagonal. And then to find the eigenvalues of this sub 2x2, you would subtract the lambda multiplied by the identity matrix so that you'd have 1/4 a minus lambda minus 3/4 a minus lambda. And then you take the determinant of the matrix and solve for your lambda values. After doing so, we are given these first order energy corrections. And these correspond to your energy eigenvalues that are due to the perturbed Hamiltonian.
Talk more about putting the Hamiltonian matrix together and finding the eigenvalues for your perturbed Hamiltonian eigenvalues. The last thing we wanted to talk about while on the topic of perturbations in energy are allowed transitions for our states. And basically a big postulate in all of science is that if something can happen, most of the time it will. And so when a particle is in an excited state, it will drop an energy state if these selection rules are satisfied. And what these selection rules state are that your delta S, your spin, must be 0 from your initial to your final state. And your L value actually must change. It must either go up or down by 1. And lastly, that your J value can either go up or down or 1 or stay the same, but it can only stay the same if they're initially not 0. So if all three of these rules are satisfied, then you can have a transition from an excited state to a lowered state. And so from that it comes Fermi's golden rule, which actually tells you the rate at which this transition will occur. And basically it's a constant 2 pi over h bar squared multiplied by this matrix here, this matrix element, where V naught is an operator that's dependent, I believe, on your Hamiltonian. And so how this operates on your initial state, and then you take the bra of your final state on that, will tell you the rate at which, or if this inner product is 0, that'll tell you that one of these selection rules were not satisfied, and Fermi's golden rule will then tell you that the transition rate will be 0. And then lastly, just to give you guys a quick little example of this, if we are initially in the n equals 2 state for a 2p3 halves particle, we can see here that L equals 2, J equals 3 halves, and S equals 1 half. And so an allowed transition would be to the 2s 1 half. Our energy dropped from 2 to 1. Our L went from P to S, which means from 1 to 0. Our J value went down by 1 from 3 halves to 1 half, and our delta S was 0. I think I mentioned that, sorry. And our delta S is 0. So this satisfies all three of the transition rules, so this state can happen, or this transition can happen. And yeah, so those are the selection rules for electric dipole transitions. Merry Christmas, Chad. Here's some photos of Connor as a kid.